You're from Barcelona, the Supercomputing Center, and I guess one of the clusters that we were talking about earlier on around you. And I'd love it if you could talk a little bit about your own processes and systems at BSC and what practical problems you're trying to overcome that other people can't. What are you addressing there?
Yeah, so we are a research or academic outfit. We are the National Supercomputing Center. So our remit is not to do any products, but to do research. So what we do that commercial chips don't do, what problems we solve. So I would like to give an external example. We do blue skies research, or what would be perceived to be blue skies. And this is, for example, if you look at how ImageNet was developed in the first, let's say, 2000s, and then there was some dormant period, then news broke out that AlexNet achieved, immense performance compared to the other solutions. And that was in 2012. The same year, a colleague of mine, he published an article on how to build an accelerator for this kind of neural networks. And the example that was given yesterday dinner, the TPU, the Google TPU, appeared 3 years after this, let's say. So what we do is we take up topics, we notice things that are not maybe, that companies don't want to do because they don't probably have the resources, they don't see maybe the market, or they think that it's too far in the future. And then those become relevant, could become relevant over time. And in fact, the person who wrote that article, Olivier Temam, he's now working for DeepMind. So after that, they kind of like, the companies absorb us, as far as what we are doing in BSC, we are doing high risk, high reward research. And an example of that, well, you have the chips that we have. I put the photos of them. We have done about 10 now. And we are doing things that are probably not very fashionable. Example is vector processor. So vector processor like the Cray of the 1970s, the supercomputer, which is not a GPU. It has a different way of working with instructions that are very long, unlike GPUs where they have a different way of working. And you might say that GPUs are good, and then why do we do a vector processor? Let me give an example. The matrix multiplication was mentioned. So for supercomputing, there are two types. One is the dense matrix multiplication. That's where the top 500 of the fastest supercomputers are listed. Jupyter, an example. And there is also a sparse matrix multiplication. And there are two types of sparse matrix multiplication. One that is used in AI, which is kind of like a sparsity of maybe 40, 50, 60%, and the one that is used in HPC, a sparsity of 0.001, like it's very, very sparse. And if we list the machines there, the vector processor, our design, is 5 times better than the top GPU in that list. It's still miserable because this top GPU, number one in the world, can do only 1% of efficiency. Think about the energy, which is megawatts. You have, let's say, 100 units of processing power, and you are using 1% of that for sparse matrix multiply. And we are we are very happy because we are doing 5x. We are doing only 5% of that. So there's a very long way to go.
Huge potential.
Exactly. So there's a very long potential for ahead of us. So for doing, for example, things like my colleague just mentioned, neuromorphic computing. So that is analog computing. That is kind of one way that we embed in our supercomputers those revolutionary technologies, and that's our job to do. We like to research on that. We do other things like, for example, unusual things, databases. They are mundane. You have those queries, and then you get results. And most of the time, again, in the previous presentation, it was mentioned memory, moving from storage to a processor. Most of the time, you get in a lot of data in databases, and then you process very little of it. So then we move the computation close to storage and avoid this burden of getting all that data and then returning some of that data into the disk. We do bioinformatics acceleration. It was mentioned short reads. Now we have long reads. So Illumina machines had short reads. We have long reads, and we have a combination of that. And then we develop hardware, let's say, techniques so that the processor works equally efficiently with both type of reads. And post-quantum, when we look at the post-quantum side, the algorithms that are proposed are very compute intensive. So we also design accelerators for post-quantum cryptography. Homomorphic encryption. So you encrypt things, and then in the normal encryption, then when you need to compute that, you de-encrypt that, because you cannot compute with encrypted data. Unlike homomorphic encryption, which you can compute with encrypted data, so your data is never de-encrypted anywhere inside the processor. That technique is like maybe millions of times slower, so we accelerate that maybe 1,000 times, but still we are 1,000 times slower. So we do those kind of, I would say, quasi crazy things, and there's a long way to go, but we propose some solutions for that. Last but not least, I want to mention the in-memory computation. That was, I think, a key if we want to move forward, moving the needle, efficiency needle especially. And I think there is, I don't need to mention more, because I think it was already, I think the case has been settled, but I think there are still system challenges related to, for example, in-memory computation, because your CPU is doing something, and then you are also doing some other computation in the memory, but then you may need to, once in a while, to say, hey, whoa, I'm doing something, but maybe what the other core is doing is maybe I need something, or I need to send something there. So what we call coherency. So this is something that is at the higher levels that is being studied, the operating system, the programming models. So we should have this system level outlook. And I would say supercomputing centers, if I could advocate a little bit shameless plug on my side, is a good place to do that, because we have hardware software co-design also conveniently already been discussed. And we do that because our supercomputers, when we are designing, we sit down with the hardware manufacturers, we put our domain scientists from bio, from earth sciences, from engineering departments, and then they say, okay, I have this algorithm, but then I have this bottleneck on the hardware. So how can you guys solve it? And the other way around. Also, on our hardware side, we we design, let's say, some features, and then we go to the software folks and say, how would you like to use those features? So as coming to the RISC-V part of it, so we are involved in large projects in the EU side, and we are many partners, but we are doing it European style, so everyone is having a little piece of the pie. It's challenging. There's lots of bureaucracy, but we are chugging along.
Yeah, well, I'd love to learn a little